Okay, so this is the second week, and we are talking about supervised learning, more specifically about classification and regression, and we will also talk a little bit more about the evaluation of models and how the learning process works. So just to recap, what the machine learning field is this subfield of artificial intelligence, where we are studying models or algorithms that can learn from data and generalize to unseen data without explicit instructions, obviously. So we, particularly when we're talking about supervised learning, and this is kind of a recap, we're talking about having a data set with variables called features, so the columns of a data set, and dependent variable, or the target, right? So the output. So usually you have let me just change the color here. Usually you have a table where you have the features, and one of the features is the target or the class, or the value that you want to predict. So we're talking about predicting. This is the features or the attributes, each column of that. So in the end of the day, through what we call a training algorithm, we will learn how to predict the output giving the inputs or the features, right? So that's what we're learning. We're learning a function that maps this columns, these features, into our target. Okay, so more specifically, when we're talking about classification, we're talking about predicting a category, right? So you could think about predicting a dog or a cat from an image. You can for example, think about an application where you want to predict the eye colors of people. There's lots and lots of applications where the target is actually discrete, categorical. Okay, so you have a limited number of categories. When the target is numeric, so it's a continuous numeric value, then we're talking about a prediction that is called a regression. Okay, so you're doing a regression. You're finding this function, it receives inputs, and then it's predicting a number. Okay, so for example, if we want to find out the the price of a house based on the square footage of the house and the neighborhood and other like the age of the house and other features, that is not a classification. It's a prediction called regression. Okay, it's not categorical labels, but actually a number that you're trying to classify. Okay, so we're going to start talking about the mother of all machine learning models, which is, so regression again, it's a continuous numeric target value, and classification is just a discrete categorical value label. This all can be just this doesn't need to be a video. This can be just a recap session, for example. Okay, because all of that I said up until now is something that they already had in the first week. So let's talk about the mother of all machine learning algorithms, that it's called linear regression. And linear regression is widely studied in all STEM courses and more mathematical based courses. And yes, it is a machine learning algorithm. It's a simple one, but it really depicts what what is a machine learning, right? So So let's try to understand what a linear regression is in its simplest form. So in its simplest form is trying to determine a linear relationship between two variables, right? So the input, for example, the experience you have, the years of experience, and you're trying to predict the salary that you're going to earn. Okay, so you're trying in the end of the day to fit an equation, to fit a line, because it's a linear regression. We have other types of regression, but in the case of a linear regression, you're trying to fit a line to the data, right? And you actually use a learning algorithm. And the learning algorithm is this: you have a data, and during the training, during the learning, you are actually trying to minimize the sum of squares of the distance between the points and the regression line. So let's say that you start randomly with this line here, right? So you start randomly with this line, and the goal of this line, so in case of a line in one dimension like this, is just it's beta x plus epsilon. You will have to find the slope of the line and what we call the bias term, right? To better fit this data. So you can see that the blue line is not fitting the data. So you will tweak the beta and the epsilon to kind of, get the line to the best fit here. Okay, so that's what we're doing in terms of learning. The learning algorithm will get you from an initial random line where you're going to randomly assign initial values. So this beta and epsilon, and we can also recap the line equation as a read section, like point them to some kind of a reading that kinds of recaps the equation of a line. But you will randomly assign values for beta and epsilon, which is the slope of the line, and the intercept of the line, the point that the line intercepts, it's this. And the slope of the data is beta. So how steep is the line. But anyways, during the learning process, you are actually updating the beta and the epsilon. So you're really kind of you're kind of turning the line and you're fitting the line in order to make this difference, so the difference between the point and the line, minimal. Actually, it's not the difference between the point and the line, but it's the squared difference, right? So every training algorithm is an optimization process. Okay, so all machine learning, during learning, we're doing an optimization process. Okay, so you're optimizing beta and epsilon to get this little differences here, the squares of these little differences minimized. Okay, why is that? Well, because because we want to generalize to unseen data. When you want to know a new point of your data set, so you're getting you are hiring a new person, and you want to kind of estimate its he or her salary. You will kind of put the experience here. You will hear, oh, the person has 10 years of experience, how much it will earn. Well, I go and I look up the result in my line. Oh, my salary will be $10,000, okay, or $100,000. So That's and maybe you didn't have this as a point, right? So you don't have, when you have 10 years of experience, you didn't have that specific data point in your data, in your historical data. This is kind of a new information. So you're just really seeing the result in this regression line. If you have these blue distances, these little blue distances minimized, you have a better fit. Okay, and the reason that it's squared is because this difference here, for example, is positive and this one is negative, and I don't care about it. So that's why I square, because I want this differences, even positive or negative, either positive or negative, to be minimal. Okay, so the training algorithm is an optimization algorithm, and it has a loss, what we call a loss function, meaning that during training I want to minimize the loss function. In this case, for linear regression, the loss function is actually the what we call the mean squared error. It's this function here. Okay, so during the training I am minimizing this loss function to do the better fit. So I'm choosing this beta parameter and this epsilon parameter while minimizing this loss function, and this will give me the better fit, the best fit. So it is very important now for us to define what is a parameter and what is not a parameter, or some kind of a nomenclature that appears a lot that is a hyperparameter. Okay, so a parameter, it's actually a model parameter. It's a weight, or it's a value inside the model that you have to learn. So in this case, it's beta and epsilon, right? And we are set before, we are set during, these values are set during the training algorithm, and they are updated. And then finally, when learning stops, you will have a value, for example, for the slope, beta, and for the intercept epsilon. Okay, for example, this is a linear regression in just one dimension, meaning that you have only one experience, only one feature, and it's really simple. You have only two parameters to learn. So this is another definition that I just said, and I think it's worth to kind of go through. It's a dimension or dimensionality. It's the number of features in the input of the model. Okay, that you will use as the input. So in this case, we have only one parameter, so it's a one-dimensional model. You're only kind of taking the experience and outputting the salary. Okay, if you were to see this as a data set, you would have the experience, a column of lots of experience, and the salary as the target here. And you would have, so this is a one-dimensional data set. So the other term that appears is the hyperparameter. Right, so this is very common in terms of hyperparameters, and we will see it a little bit more specifically of what it is. But hyperparameters are configuration settings to control the learning process. Okay, so we will see that this is, for example, the rate of update. How quick you update this parameters of the model, what we call the learning rate. And we have several other types of hyperparameters, and we will discuss that. All right, so you actually choose the hyperparameters before the learning starts, and it's actually it will kind of control the learning process. And it requires experimentation. You can learn the parameters of the model using a set of hyperparameters. You can learn using another set of hyperparameters. This will change the final values that you will find, and is an experimentation kind of. It requires experimentation from the data scientist. Okay. All right. So again, this little example here is for one dimension, but you can have more dimensions. For example, you could try to let's say that you could try to predict the overall height of a person using the person's arm length, right? So this also would be a one dimension, and a simple regression model would say, okay, when a person is around, when a person, like for example, let's say you have the arm length and the height. You have several historical points, and you're kind of getting the overall trend. And this line will actually say, oh, for every 20 centimeters of arm length, well, actually the height gets 30 centimeters of increase. Okay. Now, to get the model more accurate, you can include more variables. So you can get the dimensions up. So you can say, well, the first variable could be the arm length. The second variable could be the biological sex, if it's a boy or girl. Another one, an X3 here could be if the person is athletic or not. And these extra inputs will help create this multi-dimensional model, in this case 3, that better captures the variations in height. And you will always have the intercept where the line crosses. And again, in 3 dimensions, we cannot see the graph. I cannot kind of show you a figure of a graph of this line in 3 actually in 3 dimensions I could, but in n-dimensional problems I cannot show you this line, but it is what we call a linear combination of these features. Okay. All right, so this is the first, and it's very important to learn about linear regression, because it really is a very simple model that we can kind of pose all these definitions: hyperparameters, parameters, dimensions. What is a training algorithm? What is a loss function? Again, this loss function, just to kind of finish here, is an optimization cost, right, or loss. So if you want to minimize this differences here for all points, so that's why you're summing all of them. The less the smaller this value, the greater the fit, right? So that's what we're doing. You can choose different loss functions, okay? And during training, for linear regression, the mean squared error is kind of the commonplace loss function, but the loss function can also change, and you can tweak the loss function, whatever you're doing, but that's essentially what it is, okay? All right, so now let's talk about logistic regression. Logistic regression is one of the most, it's a variant of linear regression, and then probably the most basic classification algorithm. So linear regression is actually used, so just go back a little bit. Linear regression is actually used for regression, all right? So you're outputting the height, which is a continuous value. It's not categorical, and it's used for predicting a number. For logistic regression, although the name is regression, and we will see why it's a regression, but in the end of the day is used for classification. Okay, so although the name comes and brings it regression, this is used for classification. Okay, instead of fitting a line to, for example, numerical variables, that is presumably has a presumably linear relationship, you can predict a categorical output, right? So here's an example. We want to predict the, let's say that we want to predict imagine we want to predict whether a fruit is an apple or an orange based on two features, its weight and its color, okay? So for example, it's a numerical scale. Let's say that when it's greener, the score is lower. When it's orange or reddish, the score is higher. So we would have a data set like the color and the weight, and if it's and the class. If it's, so you have several data. You're learning from historical data, and as soon, so this is orange, this is apple, this is orange, this is apple. As soon as a new apple comes in or a new orange comes in, you want your model to classify that, right? So using a linear regression wouldn't help us because we're not predicting a continuous value. Okay, we're predicting a class. So that's why we would do a logistic regression, okay? So instead of fitting a linear line, what we do in logistic regression is we fit a sigmoid function, okay? So here, so let's say that our output is 0 if it's orange, our output is 1 if it's apple, and I'm here showing in this graph only about the color, like, because I'm just doing one dimensions to kind of show you the graph. Okay, 2 dimensions, 3 dimensions, I can show you a graph. It's a little bit more difficult, but after 3 dimensions, then I really can't show you a graph. Okay, but anyways, you want your model to, when a color comes in, a color and a weight, but here I'm just showing the color. You want to output, here's the model, you're fitting a function that when the color comes in, you want to see if you want to classify an apple or orange. So the straight line is actually, you cannot fit a straight line for different classes. You can see that some of the oranges and some of the apples, they have, it's hard to say with the same color. Let's say the color is here. With the same color, some instances of this data set are oranges, some instances are apple. They're kind of more orangish, reddish orangish kind of mixture, okay? But it's not, we're not able to fit a particular line that will give me good results for this classification. But look at the logistic regression. When we fit this function, we're going to fit this function that is curvy. It has an S-curve kind of shape, and it will predict whether Y lies within. So it's kind of this curvy thing, and it can predict. And the sigmoid function is a bounded function between 0 and 1, and it will give you a value, all right, that is conveniently put between 0 and 1, and will now conveniently tell you the probability of a new data falling into a certain class, right? So let's say that this fruit here with this color, if you go to the curve that you fitted, it has, for example, an 80%, because this value here is 0.8, it has a 80% chance, for example, to be an apple, right? So this is an apple. So the logistic regression is actually using a probabilistic fitting curve to do a classification, and you will have a threshold, right? So you will say that things bigger than 0.5 are apple, things less than 0.5 are are oranges, okay? And this threshold actually can actually change, okay, depending on the distribution of your historical data, okay? If you were to imagine that you didn't have this point, okay, so you can say that actually they're not overlapping that much, so you can with some confidence say that things bigger than 0.7 are apples. So you can change the threshold, okay? And this changing, the fit of the curve, the parameters of this S curve that I'm not going to show the equation because it's a little bit more mathematically intricate. The parameter of fitting this curve and even the threshold, you will learn. You will learn doing the training algorithm by minimizing a loss function of the better fit, right? In this case, for classification, we usually the loss function will always also be a mean squared error between y1 and y0. So when we're passing this to a training algorithm, what is orange is 0, what is we actually transform this class to a numerical value, but it's discrete, right? It's not continuous value like height. It's discrete. It's a category 0, category 0, category 1, category 0, category 1, category 0, category 1. And we will also minimize the loss function. We will choose a loss function that in this case is the mean squared error as well. So for example, let's say that the result of this new thing should have been an apple, but it outputted 0.3. And we know that 0.3 is an orange. So it should have output 1 and it output 0.3. So you have a loss of 0.7 and you want to minimize that loss, okay? All right. So the other algorithm that we have is what we call k nearest neighbors. Okay, and although this is considered a machine learning algorithm, it actually doesn't have a learning. It doesn't have a learning step. It's what we call a non-parametric algorithm. Okay, so we don't have to fit anything. We don't have to. This is kind of it's a machine learning algorithm by. Because it's used for classification and or even regression, both of them, but it's actually very simple, and it's considered to be a machine learning algorithm just because it's used so much, but it doesn't have a learning step. It's called non-parametric, and actually we use it on the go. So the idea is simple. Right, so giving a new data point of your, for example, a classification. And here's let me crop this. This is copied from somewhere else. All right. So so this is K and N. K nearest neighbors. So let's say that you have male and you want to predict if a person, you want to classify a person of a male and female, giving the height of that person. Well, one way to do it's to learn, for example, a logistic regression. The other way to do is actually to say that the gender of the person, the new person, will be the same as the majority of the 5 people closest to the 5 people closest in height. So you're analyzing the height. Let's say that the height is this one here. Is this height here for this new person? Let's say 179 centimeters. And what you do is you analyze the height of the 5 closest persons. So what are the 5 closest persons? This 1, 2, 3, 4, and 5, right? So these are the closest persons that has these heights, and then you will say that you will assign the class of the majority. So the majority are males. You will say, okay, this person is also male. It's a very, very, very simple kind of algorithm, and it's called K nearest neighbors, and the K is actually this number that you set that you set, right? It's a parameter of the algorithm. Because we don't have a learning, you won't learn. You will experiment with it, okay? And you can also you can use it for classification. You can use it for regression as well. And for example, as regression, you want to determine you predict the chest circumference giving the height of the person. Let's say that a new person comes in and it has a height of I don't know, like as a 50.5, right? And then you will see, okay, this is a 3 nearest neighbors, so the algorithm will say, you'll say, I want to predict that, so the height, the chest circumference of that person will be the average of the 3 closest people, right? So if this is not height, this is, okay, let me start again. This is the height, let's say 180 centimeters, and you can see that I want the chest circumference. That's what I'm predicting. What I'm going to do, I'm going to take the average of the 3 people that has the closest heights. So this person has 181, this person has 179, this one has 180.5, and they have 50, 55, 51. I will do the average, and I'll say that this person has a 52 average. Okay, so this is called the K nearest neighbors. And although it's very simple, it can be very, very effective still, okay, to do classification and regression. Okay, so now let's see another model. Another model is called the support vector machines, and this model is a machine learning, a proper machine learning algorithm, because it has a learning step, right? And it was originally designed for classification tasks, but it can also be used for regression tasks. And the core concept of the algorithm is to draw a decision boundary between data points that separates the training set, right? So if you draw a decision boundary that separates the data points that you're training on, as a new unseen data point comes in, hopefully you will possibly classify it with a good efficacy. Okay, so let's say that we're trying to classify animals by their weight and length, right? And so we have a 2-dimensional problem. We have the length of the length of the nose and the weight of the animal, and you want to kind of say if they're cats or elephants. Okay. Well, the SVM will kind of create a decision boundary, right? And it could be the simplest SVM is actually a fit of a line. That's the simplest. The SVM algorithm, the simplest decision boundary that it can trace is a line. Okay, so this line that it's tracing can separate perfectly cats from elephants. Okay, and the way it does it during the training is it maximizes what we call the margin. And let me redraw because it's so here is a line, and this is the line, and what we're doing is we are during training, we are maximizing what we call the margin, or so this is what we call the margin. Is the space between it's the space between points of the difference, the external points of different classes. So these points here, they are the most external ones of each class, and you want to maximize the space between this one and this one. So you want to maximize what we call the margin, okay? And the support vectors, they can, so the loss function in the training of support vectors is the size of the margin. We want to maximize the size of the margin. This is an optimization problem as well, and you want to maximize this margin. But it doesn't only do lines. It could do any kind of decision boundary. For example, this one is circular. It could, even if you want, like if this is a simple example and it's very separable with a line, but let's say that you could also do this kinds of decision boundary, okay? Meaning that if a new point comes in, like let's say this, you will say, oh, it's upward of the decision boundary, so it's an elephant. Or, oh, it's here, so the new point came in, it's downwards this decision boundary, so it's a cat. You can do a circle, like here in the right-hand side, right? So, for example, you can have you can have, I don't know, like apples and oranges, and the weight of the oranges and the colors of the oranges and the apples, and you can see that no line could separate, could draw a boundary between these classes. The SVM can actually draw these crazy boundaries, and in this example, it's drawing a circular boundary. Okay, so SVMs are very powerful. And to do this kind of squiggles or circle boundaries, we use what we call kernel functions. But this is out of the scope, and but it because it creates these curves, you can also use it for regression. Okay. So in the end of the day, you can fit this decision boundaries as lines, as polynomials, as circles, as several different functions. Okay, and it's a fairly simple classifier with no all the classifiers up until now, they don't have lots and lots of computational burden, because they're simple algorithms. Linear regression, logistic regression, support vector machines, KNN, it doesn't even have a learning process. So they're computationally very efficient, and they are very good classifiers and regression mechanisms. One other classifier is what we call the naive Bayes. Actually, there's a family of what we call Bayes classifiers that are probabilistic classifiers. So they come up with the probability of something being a class or not, just as logistic regression. I'm showing the naive Bayes, which is the simple ones, but you have a family of Bayes classifiers that has different assumptions. Okay, so let's talk a little bit about Bayes classifier. Just something important to say here. I'm using an example with some bad words here, right? We have to kind of come up with I think something that's better. Okay, it could be like because I'm using an example of a spam email, giving that you have these words in the email, but we can say I don't know, we can change these words just not to use it. But this is actually, although this has these words, it's a very common example in machine learning to show. Okay, although it has these words. But anyways, we can change that. We can come up with different words. I don't know, like you have a prize, so you could be like prize and lottery, something like that. Well, we can come up with the example. Okay. So the base family of classifiers, they are based in what we call the Bayes theorem, right? So the Bayes theorem is a theorem that is from the 1800s, and it's a theorem from statistics that tells us what's the probability of something, of a hypothesis given an evidence. Okay, so usually, and I always like to show this example with what we call a probability tree. Sometimes you can be sick or healthy, and then you can go and, so let's say you're you think you're having COVID-19, so you can be sick or healthy, because it could not be COVID-19, and you do a test. You can have a positive test or a negative test. Either way, if you're sick, you can have a positive test. If you're sick, you can have a negative test, which is not good because you will be what we call a false positive, a false negative, and you can be healthy and you can do a positive or a negative test, okay? But usually this is like this is what the tree showed the sequence of kind of natural steps. First you are sick or not sick, and then you do the test, right? But this is what we call, like, we cannot see this, right? This is kind of a hidden step. We never know, okay? So this is a hypothesis. This is what naturally happens with our bodies, but the way we the way we kind of test this hypothesis is having an evidence. So the evidence is if you have a positive or negative. So the Bayes theorem says this: what's the probability of being sick, for example, given that I was positive? Or what's the probability of my hypothesis? So my hypothesis is sick, given that my evidence is positive. So I got a positive. I could have get a positive from being healthy or for being sick. And the Bayes theorem gives me this hypothesis. Okay, so I'm not looking at the class. I'm not looking at the class of being sick or being healthy. I'm looking at an evidence. And the Bayes theorem is a theorem that gives me this answer, right? So this is the nomenclature, is what's the probability of being sick given this dash here, this upper, I don't know how you call this, is what we call the given that the evidence is positive. And you have an equation, right? I'm not going to go through the equation. I'm just leaving it here. We could actually point the student to, I have several videos that I use in my lectures that are very good. There's lots of other videos that you can point out to the students to kind of understand the Bayes theorem better, okay? But in general, this is what the Bayes theorem will give you. It will, given an evidence, it will give you the probability of the hypothesis, right? It will give you for example, the probability of being sick given that you're positive, and the probability of also being healthy given that you made a positive exam, right? And they have to sum up to 1. Okay, so if you have one, you have the other. So you have the classification. In the end of the day, you have the classification of your things that you're not seeing. And that's, for example, what we do with spam email. So, for example, what's the probability of an email being spam, given that the evidence, so that's my class, and like this is the hypothesis. It's naturally an email is a spam or not a spam, but I cannot see that. It's kind of hidden to me. It's the question that I'm hypothesizing, and the evidence is that it has penis and Viagra, for example, right, or the lottery and prize, and several other words, right? So there's a formula that given by the Bayes theorem that will give you this this value. For example, here it gave me a 92%, a 92.8% of being spam. So and then you use this as a classifier, and this would actually be 7.2% chance of being not spam. Okay, not spam. So this is the not spam, the naive Bayes, and it's called naive because this particular classifier assumes that all the evidence are independent. Like the word Viagra is independent of penis, right? For example. And actually, we know that Viagra and penis in these spam males, they kind of tend to they're not independent. If you have one, it's probable that you have the other. But naive Bayes has this assumption that they're independent, right? And that's okay. It's a naive. It's a simple classifier, so we call it naive. But it's still very good. It's still very good. It's still very powerful. It's still very powerful classifier. Okay. So, and it's very efficient. It's very simple, and it has a learning. It has a learning stage. So how can it has a learning stage? So you have a data set of lots of emails. And you have columns of, lottery or prize or penis or Viagra. And you have the class of spam, which can be 0, and not spam, that can be 1. And you have several emails, okay? So you have a historical data, and you want to learn from this data. So what you will see is that if it has penis, and not have Viagra, it could be a spam. If it has not penis and not Viagra, probably it's not a spam. Sometimes both is a spam. If you're doing a treatment for some kind of disease, for some kind of problem, you could see penis and Viagra, and it's not a spam. It's an email from your doctor. So I mean, you will have historical data. And what you're going to do is from this historical data, you will learn the parts of the equation. You will learn the parts of the equation. And the parts of the equation are other probabilities. So you will calculate the probabilities that you found on your data. So there are other probabilities that you found on the data, and then you will multiply all of these probabilities and have the classification. So there is a learning step where you are actually learning some probabilities from the data set. Okay? All right. Then there's decision trees. Okay? Decision trees are very powerful, and one of the most used algorithms for classification and even regression. But here's the thing. This is the basis of a number of more complex algorithms and very powerful ones. So let's talk about it. I just want to say something before we start decision trees. There is a possibility of kind of explaining a little bit better how like the parts of the equation and how the learning works. For example, but we can do this by video or by a lecture or video lecture or a reading session. But for example, you have the historical database, you have the ones that are spent, so you know. So you can just calculate the probability of this word given it's a span, and the other one given that's a spam. And so that's what you're learning from the data, okay? And learning meaning just calculating this, right? So there's not a loss function in the sense of minimizing anything here. In other base kinds of algorithms, you can associate with the loss function. Okay, decision trees. So in decision trees, what is a decision tree, right? So again, it's very famous, and the decision trees are a series of questions, of yes or no questions, that partitions your data, right? So here is, for example, a tree that classifies if a person is low risk or high risk to, for example, a heart attack. Okay. So you start at a root node as a question, a yes/no question at the root node. So is the age less than 18? Then you have to go and look at the weight. If it's less than 60, it's a low risk. If it's more than 60, meaning that it's a young person but it's obese, then it's a high risk, right? Not obese, but overweight. If it's between 18 and 30, it's low risk anyway, and so on. So what the model, when a new data point comes in, so let's say that you have a data set with the attributes age, so you have age, smoker, and weight, right? Weight. And here if it's low risk or high risk. Okay, so you have several instances in this data set, and you will learn to find these parameters of these questions of the tree, right? And when a new person comes in, let's say it's an 18, it's a 30 smoker, so 1 for the smoker column, and a weight of a weight of 60 kilos. You will then go through the model, and you will have your answer. So it's more than 30. So let's say 31. It's more than 30, and it's a smoker. So you have a classification of a high risk person. Okay. So during the learning, so what's the thing to find these splits, right? To find these parameters of splitting the data, the way the algorithm does it is by the loss function is actually being to maximize information gain. So I'm not going to explain what is information gain. So let's say that you have a data set that has outlook, windy, humidity, and temperature, and the class or target saying that you can play or not outside, yes or no. So outlook can be sunny, overcast, or rainy. Windy can be false or true. Humidity high and low, and temperature hot, mild, or cold. So the learning algorithm will start recursively testing what is the best root node, where to split, where to ask the question. If it starts asking the question of how is the outlook and branching on the possible answers of sunny, overcast, and rainy, it measures an information gain of 0.247 bits, and it's a fractional number, like it's not, but it's okay. It's just a metric, okay. If it tests on windy, like should I ask first? The first node of my tree should ask if it's windy or not, if it's humidity, or if it's temperature. So in the end of the day, we will choose outlook because it has the higher information gain, meaning that if you take a look at the results, right? If you branch, the algorithm will branch and will analyze how many instances you will have in each category, right, of Outlook. So for example, if it branches on Outlook, 2 instances of your data set is yes, you can play, and 3 are no, you cannot. If when it asks the Outlook and and you say, oh, it's overcast, actually you have 1, 2, 3, 4 instances that are yes. And when you ask Outlook and you're rainy, you have 2 instances that are rainy, that 3 instances that are rainy that you can play, and 2 not. So you can see that the information gain has to do with the pure nodes. So look at this. When I branch in Outlook and it's overcast, it means all instances that are overcast means that I can play. So the better the tree, the better the pure nodes come out of my branching, the better the tree. Okay, so you can see that this has not resulted in a pure node. This has not resulted in a pure node. No, 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 no. So obviously this one is the one that gives me more information. Okay, so your tree will start branching in Outlook, and then it will continue asking questions. After Outlook, should I branch in temperature? Right? Should I branch in temperature? Should I branch in windy? Should I branch in humidity? And we'll calculate this information gain. And again, the gain here of humidity is the best one because it resulted in a pure node. You can see here, right? And so this is how the algorithm works. It's maximizing, it's an optimization algorithm that is maximizing this information gain or maximizing the trees that have pure nodes. Okay, so if we go back to here, the algorithm during training learned that branching first at age gives you a better tree, better classification. So it branches first on age, and it has discovered in the algorithm that less than 18 is where you should, this parameter and this parameter and this parameter was learned. And after that, it's recursively tested to split on weight of smoker, and it chose weight and so on. Okay, so the splits is how pure you have a node. So you can look at here, you have the instances of for example, low risk or high risk. If you choose a split here, you actually don't have pure nodes. So this tree is less informative. It does a poorer job than the one on the right, where you have pure nodes. Okay, so that's how the training works. Okay, and it's based on information gain. And so now I want to talk about ensemble algorithms. This very basic algorithm of decision trees can turn out to be a very powerful one when you combine many decision trees together. We call it bagging, right? Where, for example, let's talk about, I'm going to talk only about random forests. I don't need, so when we're doing this image, you can take out of this. So an example of ensemble algorithm is what we call a random forest. And random forests are actually several trees, so multiple models that actually vote on the classification of your data, and by the majority of votes, then you can classify your new data. Okay, and they are very powerful, and they can actually be used both for classification and regression. And the way to do this is if you if you zoom in a little bit, you will see that the trees will vote on the different classes, and they are different trees. And the way you kind of come up with different trees, and that's why it's called random, is that you exclude some nodes of this trees randomly, right? So one of them will have different trees will have different nodes that you've excluded randomly. And this will give you different trees with different characteristics, and you put them all to vote on the class, and by the majority of votes, you can actually do the classifier. Okay, so the training algorithm, it's you train individual trees, as we said about the information gain, and but randomly kind of cutting or pruning some of the nodes, and then you make this voting kind of scheme after. Okay, start neural networks. I want to present you with the basic unit of a neural network that I will call a unit right now. You can call it neuron. It is basically inspired in the human brain, meaning that in the human brain you have these units that are connected, and you can you can have different neurons that are activated or not activated in the human brain. So this is how we kind of modeled this networks of this units that we will call neurons in mathematically. Okay, so I will start with the most basic unit. So it's not a network yet, but it's a one neuron. Okay, so the neuron is this kind of circled thing. You can call it a unit, and this unit performs a mathematical calculation. Okay, and this unit has these arrows here that you can see that they receive an input, for example, x1 and x2, and so let me just change something here that's important. x1 and x2, x1 and x2. Okay, so the representation, this is a graphical representation of this unit, and this unit or neuron will hold a value, right? This is done inside a computer. So in the end of the day, this is what is happening. You have each unit of a network. In this case, we don't have a network yet, but it will hold a value. Okay, and we will call this value an activation, if it's active or inactive. Okay, so let's say the first depiction of a network is this one here on the left. Of a neuron is here. So you have an input, another input. You can see that the calculation that the neuron is performing is actually, it's getting the first input, x1, multiplying by w1, we will call a weight, getting x2, multiplying by w2, which is a second weight, and summing up what we call a bias term, or you can think about this bias term w0 kind of multiplying 1. Multiplying, no input is being multiplied, but it's actually being used by this round unit named a neuron. So the neuron, the calculation that is a neuron. So inside the computer, a neuron is actually doing this. It's this equation. It takes x1 multiplies by w1, takes x2 multiplies by w2, takes w0, which is a bias term, and applies a decision, or what we call a function g, to this sum. Okay, to this linear sum of inputs, and this will hold a number. This will have a result, and this result the base, this result is a number that this neuron will hold. So let's see what kind of learning. So a neural network is a learning algorithm. It will learn the W's that you have here. So this is the model parameter. And the way it learns is through data, okay? And historical data. So let's say, start with actually this one here, okay? This data set. So this data set tells you if your mom authorized you to play and your dad authorized you to play, and if you should play or not, okay? So if you think about that, this is called the OR data set. So mom did not authorize you, dad did not authorize you, so you shouldn't play because nobody did authorize you. But mommy did not authorize you, but if daddy authorized you, then you can play, right? So 0 for mom, 1 for dad, you can play. 1 for mom, 0 for dad means that mom has authorized you, so you can play. And if both authorized you, then that's awesome. Both of you gave permission and you should play, okay? So let's see how one simple neuron could actually learn to this function here, learn from this historical data, okay? And we will do it by hand so that we understand the calculation. All right, so what we have here is, so I'm going to set this, I'm going to set some weights for you so that you can see that this works. And I'm kind of doing the learning process by hand, but you will understand. So let's say that you did not authorize and dad did not authorize, mom did not authorize, dad did not authorize. So this is 0 times 1. This is 0. This is x20 times w20 minus 1. So the number that the number here is minus 1. Okay, and we actually are applying a function on top of that, what we call a decision function or an activation function. So if you think about this, activation function is usually called the step function. And if it's minus 1, actually it's the value is here on its way to the left, and the result, the number that your neuron will hold is 0. Okay, so I learned how to do this, and you can test all other options. So let's say that at a point, if any one of the two dad or mom authorize, you will have, what changes will be that one of these terms will be 1, and 1 minus 1 will give you a g of 0. And you can see that a g of 0 is actually, it is here, and then you can go play, right? You can do to the other side as well, like x1, 1, and x2, 0. And if both of them authorize, you can see, if both of them authorize, you can see that this will be 1 plus 1 here, minus 1, so the result is g of 1, which is way to the right, right? And then you can also play. So we learned how to kind of to replicate this function with historical data, and we learned these weights. I mean, I put it this weight because I already know that this weights solve the problem. But we didn't need to do it manually. We could have trained this mathematical unit. Okay. You can also think about doing another function, right? You could achieve another function. For example, this function. So it would be like this. The x1 would be mom authorized. You play, and it's not raining. Right? So this is mom authorized, mom So you can only play if your mom authorized it and it is not raining. Okay. If your mom authorized but it's raining, you cannot play, right? So you can also and this will take time, and I'm gagging a lot, but this is how we will do like the explanation. You can also learn to do the end function, and the way the neuron or this unit would learn would be, and so we would delete this. Okay, and this would be a square. I have to change this image. This is a square, so this is just for me, my reference. But anyways, so in the end of the day, you would be using 1, 1, and -2 as the bias. If you do that, you can test if it's 0 and 0. This will be 0 and -2. You cannot play because you're extremely to the left here. So that's this case. If one of them is 1, it will be 0 times 0 plus 1. So 0 plus 1 -2 is still -1. So you still don't play. And the only way this output will be 1 is if you have both of them, both of the inputs. Okay, both of the inputs 1. So 1 times 1 is 2, -2 is 0, and then you activate the neuron. Okay, so the final value that this neuron will hold is 1, meaning that it will be only activated when both inputs is 1. Okay, so this is the basic perceptron, and I'm using very easy functions, but you could use functions with 3 inputs. But in the end of the day, this mathematical unit is doing W1, it's doing weight times the input, plus weight times the input, plus weight times the input, plus a bias, and applying a decision function, right? Meaning that, so if the value it holds is 0, we say that this neuron is not activated. If it holds 1, it's activated. So trying to kind of mimic a activated neuron in our brain. Okay. Now we know that this activation function, the step function, is like the simplest one, but we don't tend to use it. We tend to use the sigmoid function. We tend to use like the sigmoid function, which is this one, that gives you kind of more of a probabilistic classification, right? So, and we tend to use the sigmoid function because it is differentiable and has some mathematical reasons. Okay, we can use other activation functions as well, like as ReLU and other activation functions. Okay. But this is the basic unit. It's a mathematical unit of the neural network. Now, this neural network is all connected, right? It's all connected, and it can learn. You can connect one unit. So here are the inputs, right? And you can kind of connect. I'll make these figures better, but you can connect one unit of a neuron in one layer to other units. This is called a multi-layer perceptron, right? And the multi-layer perceptron is very powerful because every neuron from the previous layer is connected to one neuron of the next layer. So this neuron here is connected to all previous ones, and the number that they are holding will activate or not this neuron. So the numbers that the neurons are holding here, they serve as inputs to the next one. Okay, and if you think about the bias term, this W0, is responsible for kind of setting a strength of activation. if you think about the OR, when you have 1, 1, 1, 1, 1, the sum, the number sum is 2, so it's more activated, okay? So it controls how strong the activation is. And the weights are kind of weighting in the inputs, okay? So we are kind of doing this classification, and it also can be used for regression, okay? We can, and then the multi-layer perceptrons can learn way more difficult and more intricate functions than just an AND and an OR function, right? Because the AND or the OR functions with only one perceptron is actually kind of, you're kind of learning a linear decision, and you're just applying the classification function to it, right? Multi-layer perceptron is this. Like one way to understand neural networks is also working with images, right? So let's say that you have handwritten digits and you have to classify them in the number that they represent. For example, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. You could use a logistic regression, but it will be very difficult because the logistic regression takes the input and fits this kind of squiggle to classify. Obviously, I'm showing a classification of only two classes, right? A or B. But you can imagine that it's very it's very difficult because you rely too much in the input. Meaning that the input has to be informative, right? So when you fit this squiggle, you as we fit with the arm length and the height of the person, you know that the arm length is kind of an informative feature, right? And then the fit, if you do a good fit, your classifier will be a good classifier. But look at the beauty of neural network is that with their training step, you can actually, the importance of the feature and the feature selection, manually selecting a feature is not that necessary anymore. That's the beauty of neural networks. So think about number 1. Say that this is a grid of pixels, and somebody wrote number 1 here, right? So it has this pixel, this pixel, this pixel, this pixel, and this pixel, with values 1, right? And the other pixels are value 0. If you were to consider the inputs exactly this pixels in pink that I'm kind of highlighting, and you could fit a squiggle and your classifier would be good, right? But the thing is that different people write 1 in different ways and in different spaces. So for example, I could have wrote 1 here, right? And then if I'm selecting this features in pink, I will actually say that this is, like, I don't know what number is this, because I'm not even activating the neurons that learned, the neurons that needs to be activated to output number 1. So you have all the pixels of your image. These are the inputs. They're connected to several other neurons, and in the end of the day, you want a final neuron to spit out number 1, right? So there will be patterns of neurons that will be activated that will activate this class number 1 here. Okay. Oh, sorry. I think. So a good example of showing how deep learning is good with feature extraction and it helps eliminate the need for feature extraction, meaning that you don't rely on a specific set of features. For example, in the past, to do X-ray diagnosis, you inputted all these pixels from an X-ray to, for example, a logistic regression or an SVM to diagnose pneumonia. But actually the doctors, they not only the doctors but also feature extraction algorithms, they had to be kind of, you had to have this feature extraction step, and they discovered, and using the domain experts as well, like the doctors, that for example, for this region, for A, the angle between this line and this line, and the angle of other lines, and the gradient of the color gradient from other lines are important for diagnosing. So given these attributes, right? Given these attributes, the like the logistic regression, the SVM, or other kind of machine learning classification algorithm will come up with, oh, it has pneumonia. The person has pneumonia. With the advent of deep learning, you won't have to create these features. You won't have to do feature extraction and engineering and then use it for classification. You will input the pixels of this image, the raw data, the intensity, the color intensities, the pixels of this image, right? And the deep neural network will learn from these raw features, right? So this capacity for eliminating the knowledge expert is what makes neural networks and deep learning so powerful. It learns from this kind of all the features you have and from raw features. So there's this image here where I'm not sure where it is. Let me go back. This video is super good, but but before you had this feature extraction step with other classification methods or regression methods. You can actually put several features, but SVMs, for example, logistic regression and others, they kind of get confused if you have so many columns, and doing feature selection, feature extraction, kind of selecting the most important ones, then make their efficacy better. But deep learning is this kind of very robust algorithm that you don't care. It will learn from the data, and you don't even need this step. Okay. Let me go back a little bit. We can have multi-layer perceptrons can actually have multi-class classification. So just not 0 and 1, you can have several different classes for classification. For example, here, number 0, number 1, number 2, number 3. And usually the way it's done is the neurons on the last layer, right? So if you go back here, the neurons on the last layer would be several. Like, let's say that you want to classify number 1, 2, 3, right? So you would have 3 layers, 3 output neurons, and if this one gets active, it means it's number 1. If this one gets active, it means that's number 2. If this one gets active, it means that's number 3. So we can do multi-layer classifications, okay? And again, I'm showing these examples at classifications, but you can also do regression, right? You can think about the simple perceptron or the simple neuron is actually doing a regression, right? So after you calculate so let's say that you have the arm length, the biological sex, and how sporty you are in terms of sport interest, and then you want to output the height. Well, it's doing a linear combination of this, and you can actually apply a function, for example, a linear function, for example, meaning that this is actually, you are actually doing exactly a linear regression, because whatever number you have inside the parenthesis, if it's linear, will be the output. Right? The linear function is whatever is in, it will be out. Okay? So you can also use the perceptron to do regression, and multi-layers as also doing regression. Okay? For regression, because it's just one number as the output, you have just one neuron on the output, in the output, but it will hold whatever value it is. Oh, the height is 180 centimeters. Okay, but you can also do regression. So another way to kind of interpret deep learning is, and here the term deep learning means exactly this multi-layer perceptrons that has lots of layers in between the output and the input. So that's the meaning of deep learning. And the beauty of deep learning is, as I said, about the features extraction, right? So it comes in automatically. And you can learn without even thinking about selecting features. Obviously, if you do that, if you have the prior knowledge and do that, that's best for your model, but it carries out lots of information extraction on the go. So I will just give you an example. This is a figure that we have to change, but imagine that you had a figure, a 4x4 figure, meaning you have some pixels, 16 pixels, and you're actually inputting a figure of oh my God, this is of a bird, right? So in the end of the day, you want a neuron to be active that says, oh, this is a bird. Okay. This is a bird. Oh my God. Okay. And what the neural network would be doing, the learning process is doing, is think about having a input layer with 16 pixels, right, for the 4x4 picture, and the first layer of this would be an edge detector, right? So let's say that you have a neuron that identifies little lines, right? So let's say that this neuron is active when it identifies a little line. Let's say it identified this line. So the input, the combination of these inputs, and say like the figure is one, so it's a black and white figure, the background is black and the foreground is white, so the birdie has an intensity of 1 and the background has an intensity of 0. So this is an edge detector. It detected one edge, and this one, for example, detected another edge here, right? The following layer, another neuron can be activated when if it found two edges and the angle is it's a low angle between them, right? You will activate this neuron, which is a beak detector, right? And after the beak, you could have neurons that detects eyes, that detects feathers and wings. And in the end of the day, if you have a pattern of neurons, that means beak, eyes, feathers, it will output a neuron named bird. Okay, and the way you kind of set up this the first edge detector, and then the beak detector, and then the eye detector, and so on, is that, for example, I'll try to do this. If you think about the pixel here, right? You can think about having this pixel being at a neuron, this neuron here, which is the edge detector. It will activate when it sees when it sees 1 in this particular pixel. So it has a weight of 1 and 1, and in the neighboring pixels, when they are not activated, right? So when the neighboring pixels are 0, okay, when the neighboring pixels are 0 and this particular pixel is 1, you will be activating the beak detector, for example, in this position. And you can have, for each position of the image, you could have this edge detector. And now you can have this, for example, being active when 2 edges are active, right? So then this is a beak detector, and so on. So what you're doing is you are adjusting these weights to detect your class or your regression. Okay, and this could be billions of parameters. And again, deep learning means this multi-layer perceptrons that have several parameters, meaning that all these weights of connectivity are found in a learning process. Okay, so again, you have all these weights. You have the weight between this neuron and the other neuron. So between neuron 1 and 1, from layer 1 to layer 2, this one is the connectivity between the weight that this neuron 1 with neuron 2 of the layers. So it's very intricate. The name of the algorithm of the learning process is named so I changed here for a little movie, a little video, but what the gradient descent means is that it's the optimization algorithm used to train the deep learning models, right? So this optimization algorithm called gradient descent iteratively adjusts the model's parameters to minimize the errors. Okay, so let's say that for the birdie example, you start by setting up random weights to that billion parameters, right? And you so obviously, if you run this neural network, it will output whatever it is. Like if let's say that this neural network should output 1 for birdie, and it outputted 0.3, meaning it's not classifying correctly, right? Because you're showing a birdie in the input. So it's kind of classifying poorly, and you have this error. Okay, you have this error that is 0.7. Okay, from 1 to 0.3. So what you're doing is you iteratively tweak, or you kind of turn the knobs of each of that weights to minimize the error, right? Which is our cost loss or cost function that we already discussed. In the case of this kind of classification, we could use the mean squared error, right, as well. So it would be 0.7 squared. That will be the error that you have. Now, after kind of tweaking the weights a first time, your error should, in theory, and it will decrease. Okay, and then so your cost function is at each training step is minimized, and we're going to define the training step or epoch a little bit further on. Okay, so I like to show this image here. So if you think about that, think about the weights, right? The weights here, I'm showing just one weight, right? But imagine that W is like the aggregation of all the weights of a matrix, of all the parameters of a neural network. And at each time, at each learning step, your loss function gets smaller and smaller up until a point where you will reach a minimum. Okay, so I always say that this is like a hiker trying to find the lowest point, right? Or you can compare that with a ball like going downhill. Okay, I'll show you another image here. So the algorithm is called gradient descent, right? Because the gradient is a mathematical entity that shows that shows the direction, right, of the steepest downhill, right? So the algorithm kinds of tweaks, kinds of adjusts the model parameters in a optimal way, in a way that it's making the error decrease, right, in the fastest way. Okay. So for each step, for each learning step, you present your data set, your learning set, and you adjust the weights, and then your error will decrease. Then you show again your data set, and you adjust again, right? So at each step, the algorithm, the gradient descent algorithms, calculates this gradient, calculates this mathematical entity that shows the adjustments needed for these parameters to minimize the error in the fastest way. And this process continues until the model reaches this minimum or it stops, right? So it's like a ball rolling down a mountain, and it will find the minimum of the loss function. Sometimes when you train a neural network, sometimes you will get a very good fit for the neural network. Sometimes you will stop at what we call local minimum, and you have to maybe start the ball into another point where the ball will kind of find, like if you start the ball here, like if you randomly start here with your weights will be updated and will find a global minimum. So that's why during training of neural networks, we train it several times. Okay, we train it several times, starting with random weights starting with different random weights, because if you started here, you will probably find a local minima, because you found, and when you find a minimum, you stop the algorithm. But if you start here, you will find a global minimum. Okay. And one of the one of the implementations of this algorithm is called backpropagation, and that's how we implement this algorithm in neural networks. Meaning that if you go back here to, let me find the neural network. When you find, so here you go. So this is a network, a neural network. When you run the neural network the first time with random weights, all of these connections, you will have an error. Then you will calculate the gradient, and then you start by updating, by tweaking the weights of the last layer. And after that, the weights of the previous layer. And after that, the weights of the other layer, and the other layer, and the other layer. So that's what we call backpropagating. So we are minimizing the error in an optimal way, because we're using a gradient descent, where the gradient is telling us how to tweak this weights to optimally minimize the error. And you propagate these tweaks. You kind of do different adjustments in a back propagation way. So you start by tweaking this, then that, then that, and then that, then that, then that, then that, and then you run the second step. You run again the network. You will have an error. This error is going to be used for the second learning step, and then you backpropagate again. Backprop, 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 backprop. This is the second adjustment of the network. Then you show, for example, a cat or a bird, sorry, and the error is not 0.3 anymore, and it's not 0.7 anymore. It's kind of you're closer to 1. So you get again, you show the cat, you will get now, for example, 0.6, so you have a 0.2 error. So you still have an error. You calculate the gradient, which will show you that to minimize this error, you have to tweak these weights in the fastest way. And you backprop, kind of adjusting all of these layers up until you find the minimal error, right? Meaning that you can find the minimum error. Sometimes the error will, if you keep tweaking the weights, the error will go up, right? So you want to stop when you achieve a minimum. So you keep calculating the error. If you're here and the error kind of tends to go up, you halt the algorithm, you stop the algorithm so you can stay in the minimum. Okay? So we talked about backpropagation, gradient descent, but all that I've talked here was about multi-layer perceptron and what we call the feed-forward architecture. In the feed-forward architecture, we have neural networks that are connected, that the information goes from the input to the output. Let me show you this. This is a great video that I'm pointing out for more resources, but this is the feed-forward kind of connectivity. The input comes in and the neurons are activated, like the neuron in the next layer is activated up until the output. But there's so many architectures, different architectures, right? So I'm just going to kind of talk about a couple of them, and you can kind of go and search for more resources. One of these neural networks are called convolutional neural networks, and it's used for image processing, classification with images. This is the architecture that is very powerful for image processing. Okay, so that vanilla model that we talked about the multi-layer perceptron, finding a bird. That is like quote unquote old technology. They're much better architectures. The other architecture is this one, is the recurrent neural network. So you can see that the activation state of a neuron ahead of, let's say that I am this neuron, the activation of this neuron ahead of me will actually change my activation, right? So when the second, so this kinds of networks are very good to be used with forecasting time series, right? So forecasting things that happens in time. So the next steps. Why is that? Well, because, for example, let's say that the second point in time. So let's say that you have values of the stock market, okay? And the first value comes in and you want to predict the second value. You're learning, right? You're learning, you have a data set and you want to predict. So let me draw this. I think it's going to be better. Say that you have this data set of the stock market where you have a point of the stock market value and you want to forecast the second value. From the second value, you want to forecast the third value, and so on. From the third value, this is a 2. You want to forecast the fourth. So this is my target for my supervised learning. And this is the attribute, right? So this is my input. So what happens is that if we go back to that video, when let's say your first input comes in, you're learning, so you will have you will learn how to predict x2, okay? Now when x2 comes in, the value of this neuron before, when x1 was the input, will kind of change the activation of this guy. So this is what we call systems with memory. This connection here is kind of it's a temporal connection, meaning that the state of this neuron when the input was 1 will actually change the state of this neuron when the second input comes in. So you can't, this weight here is memorizing stuff. So it's very good architecture to be used with forecasting time series, okay? Like stock markets and so on. And that's it for neural networks. Several good resources here. It's very hard to kind of go in a shallow way, but I think that with all the extra resources, and obviously I will have to streamline this script and everything, we will make to continue. Now we saw some models. I want to talk a little bit more about model complexity. Okay, so the model complexity refers how sophisticated a machine learning model is in terms of its ability to capture patterns in the data, right? So a more complex model has more parameters and can learn more complicated relationship, like a neural network with many layers that has billion parameters, and a simple model like a linear regression that has less parameters. So finding the right level of complexity is crucial. And a too simple algorithm like this it's very simple. And for example, here it's an algorithm that it's you want to regress, for example, this point. So you do a regression. This could be a quadratic a polynomial, so you're not fitting a linear regression, you're fitting a polynomial regression. You can see that it's better into capturing the model, the points, the training data. And this one is very, 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 very complex. It could be a polynomial, like a high order polynomial, and you can see that it's fitting totally the data. Okay, now you could say, oh, this model is better because it's fitting the data perfectly. And that is very important. It's a concept very important because this is not right, right? If the model is too simple, it fails in capture the important pattern, right? So you can see that this pattern is more quadratic. And if it's too complex, it will learn to fit all the training data and usually noise, and it will also poorly capture the pattern, and this is called overfitting. Okay, so let's discuss a little bit more about overfitting and what's noise. So if you think about let's see if I have. So if you think about a sinusoid, let's say that this is something that you captured in a lab with sensors. So this is data, and you can see that like it is a sinusoid, and this is like the trend of the data is a sinusoid, but because of errors in the sensors, the data is spread. You have measurement errors, you can have sensors errors, and what your model should do is to ignore this spreadness of the data. We call this kind of, there's some noise in the data. If you were to have a very complex model that fits the data totally, it would be a model that is learning this kind of pattern. And this is not at all a sine wave, right? This is not at all a sine wave. So if you're doing a regression and then a new value of the input comes in, and you should output a value of a sine, this green curve will never do it. Okay, so this is overfitting the data. And if the data is actually a quadratic like this, when a new point comes in, right? When a new point comes in, you will get it wrong. You will get it wrong. Although you've perfectly fit the training data, you're not having generalization, what we call a generalization power. Okay, so we need a model that it's complex enough that actually doesn't learn the noise, right, of the data, and actually captures everything, and that not captures everything, it actually captures the trend of the curve, or the trend of the decision boundary, the curve, or whatever you're doing. Okay, so this is this is the discussion around overfitting, and having this balance is so very important. Okay, so the optimal solution will always be where your this figure is not informative. I'll do something here. So when you're training. When you're training your model, and you have your loss function, and you want to minimize the loss function, for example, what you need to do is this: you keep training, and your loss function, for example, your mean squared error in a linear regression or in a regression, or a quadratic regression, polynomial regression, whatever, is decreasing, right? So this is the loss in the training data. And you want it as small as you can. But if your model is too complex, it will be so small that you're actually fitting the noise. So what we want is that if you think about measuring the mean squared error on the test data, you want to, this is the test data. So if new data comes in, we discussed about the test data and the division of the data set. You hold out part of your data set to test your model, but you want that to, after training, you want the loss for the training data to be small, okay? What happens when your model overfits is that actually you're learning the noise. So the loss, if you're testing in a test data, at some point, if you keep learning, you're learning too much. It's like a student that is memorizing and not understanding the data, right? So the loss in the test data starts to actually increase, meaning that your generalization power is lost, okay? So one of the mechanisms to avoid overfitting is actually splitting the data into three parts: training, validation, and test. So you have a holdout called the test data, okay? And you keep that to test several models and to choose the best one, right? Giving a metric. Now, what you do while you're training, you keep assessing how your loss is minimizing, and you keep you hold out a part of the data set called the validation data set. So this data set, you will apply your model to the data set, and you will see, well, you know, it's kind of a test set, but because you use it to stop the training, it's not an unseen data, right? So remember, you always have to test your model into this, okay? This test, the unseen data. This, although it's not used for training, validation is not used for training. It's used to kind of guide the training. Okay, to guide the training. So it will actually weight in the values that you're choosing for your parameters. Okay, so in the validation set, the loss functions as you train. So this is the train time, or we will discuss the epochs in terms of neural networks. I'll bring this concept just in a bit, but the validation error drops, and as soon as starts to get up, right, because you're starting to overfit, you halt the training. You stop the training here. So you stop the training, right? So that when you have the test set, when you have let me choose another color. When you have the test set, in the test set, because you stopped when it was starting to kind of get, it's starting to overfit, it will still be a good model. So because you're stopping the training, you're using this data set kind of to halt the values of the weights here, of the parameters of your model here. It's this validation, although not using to training, it is kind of used to get your final model. So you still have to use a completely unseen model data for the test, okay? So let me introduce the concept of epochs. While we're training neural networks, we present the data for neural networks several times, and then adjust the weights via backpropagation. And each time we show the data, so each time we show the data, this is epoch 1, I have a loss. Then I adjust my weights of all the layers. Then I show the data again and I adjust my weights again. So every little tweak that I do in my weights during training is called an epoch. Okay? Now, validation is a very common, this split here during training is very common, training, validation, and test. And actually there is a algorithm called cross-validation that kinds of gets this concept a little bit better, and it does it to kind of decrease variability. So let's say that you've divided your training set, your validation set, and your test set, and you had a result of a loss, right? So let's say that your loss after training, that you have a metric, an evaluation metric of 98% of goodness, right? Your model is 98% good. We will discuss measures of goodness in a bit. And then if you change this randomly, the samples that are inside each of these groups, you will have a 96%. And then you will have a 94%. And if you keep doing, you will have a 99%. So in average, right, with different holdouts, with different kind of divisions, you will have a metric that you can use, right? Talk about something named cross-validation. And the name is, it should be named cross-testing. You can use the validation set during cross-validation, but not necessarily. So when we do training, when we do the division between training and testing, and actually you want to do more training data, the more the better, you have two problems. The first problem is that you're not using the entire data set to train. So you're holding out to this test, and this will never be used for training. So this is kind of a bad thing. And also you have this a trade-off. Like if you want to have more training data, you will have the test set small. Okay, so the way people do that is by using what we call cross-validation. Again, I don't know why, but people use cross-validation. It's called cross-validation, but it has nothing to do with the validation set per se. It is like a cross-testing. Okay. You can use the validation set, and we'll talk about that just in some seconds. So the way it works is you divide your data set into pieces, and let me do a smaller example. 1, 2, 3, 4, 5, and you will use 4 of this data sets, smaller data sets to train, and you will test here. So you will do one training experiment here. So you're going to train a neural network in this training and test. So this is one training and test. Then what you're going to do is you're going to change the division. So you're going to test here, and you're going to use other divisions, the other 4 divisions. And you keep doing that. Okay, you will keep doing that up until the point where you use all the data for training. So let's say that now you will use this one. This one is the test. So you're going to use four splits of training, and then you're testing on this one, and as well as let's say now you're going to train this, you're going to test here, right? So in the end of the day, what you're going to have is, I'm going to test here, you're going to have you can see that all the data is used for training. So you're testing on all the data as well. So you're testing in all the data, and you're doing several trainings and testing, right? So you're doing what we call K-fold cross-validation. In this case, 1, 2, 3, 4, 5. So you're doing a 5-fold cross-validation, meaning that you split your data into 5 buckets. And in the end of the day, if you think about it, this is training, used for training. You used every point in the data set for training. And also you tested your algorithm in all data points, right? So you tested here, and also in the last one. So in the end of the day, you'll have 5 trainings and testing steps, and you'll average that. So this solves the problem of having of this challenges here. And again, you don't need to have the validation set, but you can actually have one of these buckets for validation in each training and test kind of experiment. But again, you don't need to, right? You don't need to have the validation test. The validation set is used for kind of what we call the early stopping. You stop the training for not overfitting, but you don't need to. It's not necessary. It's good, but it's not necessary. And cross-validation can be used nested with the validation set or not. Okay? But this solves the problem. There's an awesome explanation here that we can use as well for the script and get a better figure for this as well. So let me just give you an example. Let's say that I have 200 data points, samples of my data set, and I will divide in 5 folds. So you can see that each of these data sets will have 40 data points, right? And you will use, so in the first testing, you'll use 40 data points for test, but you're actually using this one and then 40 data points for test here. And in the end of the day, you're using the 200 data points for testing and also the 200 data points for training. And then you're averaging this different performances. Let's say that you test and you have 98%, 95%, 99%, 89%, 71%, 1, 2, 3, 4, 5, and you average. So this gives you a better, you average this. This will give you a better metric of your classifier, and you won't rely only on a certain split. Maybe you're not lucky and you split your data in kind of a, some kind of split that your model is not that good. So that's why cross-validation is used. Okay, so we're talking about goodness of a model and metrics. So let's talk a little bit more about that to finish the lecture. For classification models, we use these metrics here. All of these metrics are important, and we'll talk about that. And for regression, there are other metrics. So R squared, mean squared error, we already talked about a little bit about that. So let's go and kind of talk a little bit more about what evaluation metrics come up in this when you test your models. And you can test different models, and you can choose the best one in this test data set. Regression, we saw already the mean squared error. I'm not going to kind of talk about that again. Just back up the video a little bit, and you will find the definition of the mean squared error. The mean squared error is it can be used as the loss function during training, and also as an evaluation metric after training the model in the test set. All right, so for regression, so you have your target, numerical target, and here's your attribute. You are fitting a line, right? The attribute and the target. You have your training points. During training, you want to minimize these distances, squared of these distances, but you can also, like, this is the training data set, but you can also use this as an evaluation metric when a new point comes in. This new point here, this is an unseen sample, and in the test set, so you know the target, what the target would be, and you get the value, the prediction from the line, but it should be here, right? And you can also use this squared distance for the metric of evaluation. So the smallest the mean squared error of your model in your test set, and obviously your test set has several points, the better. Okay, now I'm going to talk about R squared, and only those two for regression. This is a very good resource. This images is from this movie. Let's say that you're trying to predict the mouse weight from the mouse height. So you're trying to fit this line. So you fit this line, and you will have a calculation for those who are more familiar to statistics, can understand this calculation by calculating the variance of the mean and the variance of the fitted line. But there's a formula that will give you a value, a metric, right? So for example, in this line, we were able to fit the R squared metric is 81%. What the R squared means is that there's 81%, okay, that 81% of the variation around the line, right? So this variation around the line is explained by the mouse size. So 81% of this variation. A bigger R squared is better. So for example, look at trying to determine the mouse weight from the time spent sniffing a rock, right? If you think about that, this you will fit a line here, and this model here has a R squared of 6%. So you can say that the sniffing weight relationship just accounts for 6% of the trend of the data. So you see that actually the time spent sniffing a rock doesn't tell you anything about the mouse weight, right? So the largest time sniffing a rock, it doesn't have a clear relationship as this one, right? So that the largest the mouse, the more heavier it is, right? So this is r squared. The bigger the r squared in our model, the better. We can go through these formulas. In this video, they go through what is the variation of the mean, the variation of the line, and how to calculate. We can leave this maybe as a resource, okay? Okay, and now we're going to talk about accuracy. Accuracy and F1 score and ROC, AUC. Both of these are important, and I'll leave some resources, but I will cover this ones, okay? So when you're doing classification, we're talking about classification now, you can think about, let's say that you have a disease. So you have sick people and you have healthy people. So the sick people I'm calling the positive class, right? So I'm classifying it as positive, or 1, and healthy people as 0, okay? And here's the prediction. If you in your prediction, the samples that you classified in the test set as positive, and they are actually positive, are called true positive. If you predicted a positive or being sick, but actually they're healthy, it's called a false positive, right? So let's say that you predicted that you have COVID-19, but you're actually healthy, so you're a false positive. If you predicted a negative, a 0, meaning that you predicted that the person is healthy, and that person is indeed healthy, this is a true negative, right? So you predicted that you don't have COVID-19 and you are healthy, so you're a true negative. And finally, if you predicted negative and you're actually sick, then you have a false negative, right? So we can, this is what we call the outcomes of your classification, okay? So in statistics, this is known as type 1 error or type 2 error. So the false positives are that false alarm, or we call it type 1. You're doing a type 1 error. Or when you're a false negative, we call it a false 2 error. Okay, so this is just nomenclature that comes from statistics. Okay, so let's define the first metric, which is accuracy. Accuracy is this formula here, but in the end of the day, it means the number of correct predictions you made, predictions over all the guesses. Okay, so let's say here, what is the corrected predictions? Well, the truths, right? So the true positive, meaning that you corrected classified, it is positive and you corrected classified as positive, and the true negative. This is the correct predictions that I have. And divided by all the guesses, right? Because you're summing up all the possible results. So this is accuracy. So having a high accuracy is good, but it has some problems. For example, let's say that you have a very rare disease and only 1 people in 100,000 have this disease. You could have a great classifier with high accuracy if that classifier just outputs everyone as healthy, right? So you're actually having a very, very high high accuracy, but you're missing the sick cases, right? So this is one problem. Okay. I won't talk about the rates here, but anyways, the other score that kinds of prevents, it's a score that takes into consideration this this balance, right, of having a high accuracy but kind of missing up important classifications. It's the F1 score, and it has a formula with, there's some definitions here of precision and recall. I will leave it as a resource so that you can understand what is precision and recall. But in the end of the day, you can calculate the formula just using the what we call the confusion matrix. I forgot to say that this is a confusion matrix. And F1 is it's a more complete way to ask the question of whether your classifier has a good accuracy, and also kind of trades off the false negatives, for example, right, and the false positives. So in a very rare disease, what you're doing, if you're classifying everyone as healthy, is that you're actually you have false negatives, and you can't afford to have, right? You need to identify this. So you want to kind of put a weight in the false negatives. There are other cases where the false positives are kind of diminished, and this metric gives you a good insight of that. It's very good to have a visualization. So we know that let's say that you have a classifier, that the positive class is 1, the negative class is 0, and you have a threshold in the middle, meaning that the output of your classifier, if it's bigger than 0.5, you're classifying as 1. If it's smaller than 0.5, you're classifying as 0. So that's the threshold. It's the decision threshold, right? So we talked about threshold before, so you can go back into the sessions where we talk about threshold. But if you put this in the middle, you will have a percentage that are positive, that are blue, but they're kind of getting into negative, right? So this are false negatives, and these are false positives, because they are yellow, they are negative, but they're being classified as positive. So you can change the threshold of your classifier, and this classifier, for example, if the threshold is completely here, right, so or not here, but if it's completely here, for example, it means that you are classifying everyone as negative, right? So this is the case of you're missing the false negatives, right? So the threshold can go up and down. I'm explaining this in a very loose way, but this resource will be very important, right? Because it has an animation of the threshold kind of going up and down. Finally, we have what it's another very important metric, which is the AUC, the area under the ROC curve. The ROC, or the ROC curve, the ROC is the receiver operating curve. So the last concept is this. I brought back the true positive rate here and false positive rate. The true positive rate means the true positives that you got in your prediction over all positives, right? Because you have true positives, false negatives are also positives, right? Like if you're a false this is the true positive rate, because you classify the true positives as positives, and you classified the negative, the false negatives as negatives, but they are positives in the end. So this is the true positives prediction, the prediction of true positives that you had over all the positives that exist in your data set. So we want this rate to be high, right? And we also want the false positive rate to be low, right? So what is this? This is the false positive predictions over all the negatives, okay? And so we want a classifier that has this one high, this one low. Again, I think I can get this explanation better by having a good image. I couldn't find it, and I'm kind of running out of time, so I have to make this better. But anyways, the ROC curve is a curve that shows this rate of false positive and true positive, right? What we would like is a false positive rate of 0, meaning that you don't have any false positives, and a true positive rate of 1, meaning that you predicted your positives, your true positives are actually all the positives, right? Because then you're getting everything right. So if you think about that, we want a classifier that at some threshold, right, using some threshold of the decision making, and again, go back to thresholding, this is achieved at some point of the thresholding, okay? So the ROC curve will trace trace different thresholds for the classifier, and will plot, right? So for example, with the particular threshold here, you have a false positive rate and a true positive rate, and what you want is to be close to this pink curve, right? And the way you do that is you can see that the area under this curve here is the maximum, the pink one. So the greater the area under this curve, the best, okay? So if you have two classifiers, and one has this curve and the other has the other curve, this area here is less than this area here, so the best classifier is the blue one, and you can kind of pick it, okay? So area under the curve is also a very good metric that balances the false positive, false negative kind of a challenge of certain classifiers, okay? And finally, I just want to say that during training, engineers, AI engineers, machine learning engineers can also penalize, during the learning, can penalize having like false negatives, right? For example, in in a rare disease classification. So you can use the metrics, the evaluation metrics, to pick best models. And so you're comparing between models, but there are tweaks during training that can also prevent this kinds of classification challenges. But that's out of scope. So this is it for week 2. For the prototyping, what I think is that we had a 15-minute video of introduction of WECA. WECA is a software that they will use to do the prototype, or NIME. They can choose, right? They will do the same prototype or using this or that. And a 5-minute video of showing a framework or a software named Thinkable Machine. This is just for, this is just kind of showing a classification on the go. And this too, they will use to do the prototypes. And then give the 3 cases for them, like little cases, ask them to solve and to kind of use different classifiers, for example, different regression models. I'm not sure how to assess these prototypes, but we can discuss that later.